This is problem 6-6. Interesting problem here. You have a triangular load going here. You have supports at A and supports at B. We're going to draw basically a free body diagram of this thing first. So we'll go ahead and draw this. Grab just like some type of beam like this. Okay, we know at A we're going to have a force coming up here, and you can either point it up or go like this. You got some type of support here. It looks like you're obviously not going to have any load here. You can go ahead and put that on there if you want to. Get that, come back, draw that horizontal. Okay, a reaction at B is going to go up. B cannot take any side loads because only a roller. Oops, only going to be a roller. Let's write that up here. Like that. Okay, now what you're going to do with this is you're going to make this into a point load, and really what you're doing is you're trying to find out how can you take this load and find the centroid of it and just have it come down, replace it with a point load. So I'll go ahead and label this like this. Okay, so that's what we're going to do first. Alright, so let's talk about what to do with these type of triangular loads. And I'm going to go see if I can find a triangle and maybe draw a triangle here. All you're going to do with a triangular type load is go back this way. See if I can draw a better one. Let's see if I can get better triangles here. It really doesn't matter, but so you can flip. I'll flip this thing back over real quick. Okay, the way triangular loads would work is you calculate the area of this first. So you take this distance here, and we're going to just label this as W, O, and this is going to be L over 2. So you treat this just like a calculate the area of a triangle, and that's going to be 1/2 times the base L over 2 times the height is W, and that's going to give you L over 4. That's supposed to be a W. It doesn't look like it. L over 4W. Oh, so that's what the equivalent of this is. So immediately we can come down here and put this one as W O L over 4. Okay, now let's talk about one thing too. In locating the centroid of where this load would occur, the distance from here to here will be the 2/3 of its overall length. So the length would be from here to here, but this is already L over 2, so we'll do 2/3 L over 2. And that's going to give you, the 2's cancel out, and that's going to give you L over 3. However, we know it's L over 2 here, so let's change this. We'll get in common denominators, so I can make this 3L over 6, and then since it's L over 3, we'll make this into 2L over 6. Same thing. So we know the distance from here all the way over here would be 6L. It'd be 3L over 6 plus a 2L over 6, which is this. So I'll go ahead and just draw this down to here, and then this distance, like I said, it's just going to be 5 over 6 times L. Okay, so now let's label things. This is A, and this is B. All right. So now what you would do would be you are going to take a moment around A. So if I take a moment around A, and now anything that's going to go this way clockwise will be negative. So that's going to equal to, and we want this has to be equal to 0. So we're going to say equals to negative is W naught times L over 4 times 5 over 6 times L. Again, this is force, this is distance, plus FB. You can do FBY if you want to. And now that distance is going to be L over 2 plus L over 2, which is going to be L. All right, we'll make this Y. All right, so now we will solve for FBY because we know it's equal to 0. So we can set FBYL is equal to W naught L 5 over 6 times L, and this is W, and we need to put that over 4. Simplify as much as you can. We can cancel an L out here, cancel an L out here. That's going to give me 5/24. Let me get the block real quick. 5/24 W naught times L. Okay, so that's what the what the force at By would be in terms of W naught and L. And then at this point, all we have to do is sum the forces in the Y direction. And again, set that equal to 0. And we can find out what A would be. So when I do that, I'm going to get FAY plus 5/24 W naught times L. And then we said this one was going to be W, that's coming down, W naught times L over 4. And we set that equal to 0. Okay, again, simplify that. That gives me FAY. I'll move everything else to the other side. Now we need to get common denominator, so I'm going to put a 6 here and a 6 here. That's going to give me 6 W naught L over 24 minus 5 W naught L over 24, and that will just give me W naught L over 24. Okay, so now we have this value here as FAY, and we said FBY here was equal to this value right here. Okay, so at this point we're ready to draw our shear diagram. We'll slide this on down a little bit, give ourselves some space. Alright, we'll draw a beam, or just draw a straight line here, like this. Again, this distance here is going to be represented as the total distance of L. Okay, so what happens first, we start at the left end. We know we're going to go up WOL over 24, and again, this is just, you're kind of doing this to scale the best you possibly can. And so what I'll do is I'll come up like this value here. Okay. Now what you do is you're going to go over here. Now I'm going to go over and just stop right there, and now I'm going to go over until I apply another some type of load. Now what's going to happen is I'm going to go over to L over 2, because once I get to L over 2, this load's going to start being applied downward, and it's going to decrease it. So I want to make this thing look just like it's about halfway. Alright, so we will say now the distance between here and here is going to be L over 2. Okay, now what I'm going to recommend is, before you start drawing this shape, is go to the other end. We know that B is going to be 5/24 WOL, so that has to return it back to the equilibrium point, so we can come down 5/24 WOL. So I'll draw this line down here. And again, we're going to come down a ways, because when we did this one, we said that this was WOL over 24, and we know this value here is going to be, have to go back up, of 5 WOL over 24. So technically you would want this line here to be 5 times the length of this line here. Alright, now to get where this is going to cross, you can kind of do a random slope. And basically, if you think about this too, as I move here, I'm adding more area, negative area, as I go across. So my slope has got to decrease as I do this. So what that means is that this curve would look something. Now I'm going to be off a little bit, because I'm just going to draw this. It's going to go down kind of. That's not a very good job. Let's go back again. This is really kind of hard to do. So it's decreasing in slope. Kind of like that is kind of what it's going to look like. It's a parabolic shape from here down to here. Okay, now the hard part is, and I guess I shouldn't really say it's hard, is try to find out where that little point is. Okay, so I'm going to scroll down and give myself some more room. Alright, what's taking place here? I'm going to do a rough sketch of this beam with this triangle here. Is again, you have this piece here, you have a triangle here at this end, something like this, and go ahead and label this. We said this was WO here, and this distance was L over 2. Okay, well what's happening is, I'm going to draw this in red, we only want to look at a part of this triangle, because we want, when this area here becomes the same thing as what the load is at this end, and we said the load at the other end that's coming up, label it better here, and we said that value was WOL over 24, so we'll go ahead and put that. So we need to find out when this area here is going to be equal to that. And let's talk about how to do that. So we need to find out a ratio of this height right here at any time of length of any length here. So if we take WO, we divide it by L over 2. That's really the what we're doing is the slope of this line here, the slope of this as I go up, because we got a rise of our run. If we do that, we will get 2 WO over L. Alright. So now, let's draw kind of again what's taking place. Draw this like this. So we have this triangle here. We'll call this distance here to be like an X value here. And then this is going to make this value be 2 WO over L times our X value. So again, if I take this slope and multiply it by this X value, I will find this. So now we just have to find that area and just set it to the load that's going up, which we said was WO times L over 24. Make that WO better. And this probably sounds a little confusing, but as you do more of these, it really is not bad at all. Alright, so now we're ready to go. So we set this equal to each other, so we'll do WOL over 24 is equal to this area here. The area of this would be 1/2 times the base, which is going to be X, times 2 WO X over L. When we do that, we will calculate that is WOL over 24 is equal to this. The 2's here will cancel out. And we will get X, I'll do it in black, sorry. We will get WOX squared over L. Go ahead and solve for everything except for L's, and we can cancel the WO's back. I mean, solve for everything except for the X. Move L to the other side, and we will get L squared over 24 is equal to X squared. When we take the square root, we will get X is equal to L over the square root of 24. Get the calculator, we'll run that number real quick. So 1 divided by second, square root 24. That gives me a value of 0.2041. Okay, so what that means is, again, draw the line, is that when I get over here to this distance here, again, I got this force coming up here, that when this length here to here will be L plus that. So this distance here will be L plus 0.204 L. When I get that, then this area here will equal this. So that total distance would be 1 point. I'm sorry, that'd be L over 2 too. Sorry, confusing the heck out of you. So that would be 1/2. So that would be 0.704 L. Again, when that distance becomes that and that, you have the forces balance out because this is going down like this. All right. So now we're ready to, from that, we can draw our shear diagram. And that will give us a length from here to here. Again, will be L over 2. And now we know this distance is 0.204 L. So that we know the overall distance from here to here would be L over 2 plus that, which would give me 0.704 L. Okay, so now what we know is at this point here, at 0.704 L, that is going to be where this crosses. From here to here. Alright, we also know that where the shear diagram, where the shear crosses the neutral axis, or the x-axis, that we'll get the maximum moment. So now we're ready to, we can draw our moment diagram, and we'll draw a kind of a beam of what's taking place here. Put this stuff over. So all I have to do is find out what this area here is going to be. Again, this isn't really really complicated. It's tedious, definitely. And if you label everything, it's not too bad. All right. So we know that this value here coming up is WOL over 24. We know this distance from here all the way over to back here is 0.704 L. And we know this distance here is 0.204 L. Again, all we're going to do is take a moment around this point here. And then anything that goes this way will be clockwise. So I'll call this, and call it anything you want. We'll call it point CR, call it the critical area. Alright, so if I take the sum of the moments around CR, I will get WOL over 24 times this moment arm, 0.704 L. And then this is coming down, so we'll subtract that part, minus, and we'll put this height we said was 2 WOL, and now we take it times this length, 0.204 L. Alright, so we do 2 WO over L times 0.204 L. That's the height. Now we gotta go ahead and multiply it times this length to get the force. Okay, there's the force, and now we got to do the moment arm, and we know the moment arm is going to occur a distance of what, 1/3 of this. I forgot one thing though. That's okay. When I did this one here, I took this times this, gave me this height, and this length. I need to divide all that by 2. Sorry about that. Because the area of a triangle is 1/2. So I'll just put 1/2 here. So times all that would give you the force in the moment arm. Scroll down, give myself a little bit more space. And now run this in your calculator, and here's what you're going to get. You're going to get 0.02933 WOL squared. If you do all this, you should get minus 0.0028 WOL squared. If you simplify that, you will get a value of 0.02653 WOL squared. And that's where that's going to be the max moment. Alright, so now we're ready to do this. We're ready to actually draw the moment diagram. We'll come up here. Alright, so when we do this, we can go back and look at the shear diagram. When we look at the shear diagram, we know it's going up like that. So we're going to be linear between here and over here. This part is L over 2. So we can draw a line from here all the way back up to some point here. Again, this value here, this would be L over 2. Okay, now we have a triangle, and we know that our area is going to be decreasing. So this thing will come up like this to here. This value here will be this value correct here. And then all it's going to do is going to go back down. And this thing would kind of go like this. And that's what our moment diagram would be. And again, if you need to find this point here where it's nonlinear, all you would do would be to take the WOL over 24 times L over 2, and that would give you this value here if you need that. But that's what your moment diagram is going to be.